Good afternoon, everyone. Thanks for being here today. My name is An Zhang and my teammate Qirui Qiu. In this presentation, we would like to talk about non-radiating photonics with resonant dielectric nanostructures. Before I begin, I would like to give everyone an overview of our presentation. First of all, I will give you the introduction. Then I will show you two types of them and compare the difference and the same between them. Lastly, Qirui will talk about some applications and summary. In nanoscale, photonics play an important role. In photonic research area, non-radiating source of energy has received more attention in recent years. Many remarkable studies are talking about localize the electromagnetic fields of high intensity within small volumes of matter efficiently, and we can overcome the problems of lossy by metals and plasmonic materials. So, what is non-radiating source? It means which do not emit energy in the far-field region. Non-radiating sources develop in different types. First, non-radiating state could be generated by combining classical electric. Second, magnetic dipole mode with electromagnetic toroidal multiples. One of simplest is a toroidal dipole mode oscillating out of phase with respect to a single electrodipole. We can also call it simply a nopole. Third, the complex interaction in may resonate dielectric structures. They can also support a different class of non-radiating state characterized by no energy leakage and specially localized profiles. We can also call it bound state in the continuum. Next, we are going to talk about quasi. It means very similar but not the same. There are four reasons lead to cycle to being incomplete: material absorption, finite size simples, structure disorder, and surface scattering. I would like to move on to types of non-radiating state of light. The term anopole means without poles, and it was originally proposed in the late 1950s by to model elementary particles that do not interact with the electromagnetic fields. The state could be created by a suitable combination of toroidal dipoles mixed with electric and magnetic multiples. As you can see, this is a picture about a nopole. These two dipoles can completely cancel each other by destructive interference in the far-field region and create the standing wave. The first experimental demonstration of a nopole was reported in 2050 for dielectric silicon nanodisk. In this work, they confirmed the existence of spatial conditions for a nopole state in spherically symmetric structures made of materials with sufficiently high index. As this type of structure is not particularly suited for observation under plane wave illumination, they demonstrate that by optimizing the height and radius of each nanodisk, it is indeed possible to suppress high-order multiples and observe the direct interference of toroidal and electrodipoles at the spatial frequency, which can be tuned in the visible and near-infrared. Theoretical results were confirmed through scanning near-field optical microscope. Experience with 15 nanometer thick silicon nanodiscs of diameters varying from 200 to 400 nanometers. Secondly, I will talk about bound states in the continuum. Another family of non-radiating states supported by all dielectric nanostructures is so-called bound state in the continuum. These states correspond to peculiar resonance. They are localized within an radiation continuum spectrum, while having no energy decay. Next, please look at the picture, which is about different families of states sustained in an open photonic system and their position. You may be confused. What about difference between bond state and BIC? Let's look picture on the right. The upper part is conventional quantum well, and the regular bond state is below the spectral range. When we modulate the potential of quantum well with spectrally unbound oscillations, this situation allows for localization for a bond state within the continuous spectral range. That is BIC shown in blue. I'm going to mention two main approaches to realize a BIC. The first approach is symmetry protect BIC. It's the waveguide with a cavity tuned to the frequency, for which almost of one symmetry are evanescent. Under this condition, only single frequency is allowed and cannot radiate into the waveguide. The BIC condition is fulfilled when the mode frequency lies within the continuum spectrum of radiating modes. Another of BIC is accidental BIC, originating through turning of some system parameters. They can be divided in two major groups. Fabry-Perot BIC, based on two identical resonances of two interacting cavities coupled through a single radiation channel, and Free-Jack-Winton BIC, representing the interference of two different resonances in the same cavity. These conditions can be fulfilled through the turning of the parameters of two coupled resonances when identical omega-1 equal to omega-2 and gamma-1 equal to gamma-2. In this section, we analyze the relationship between anopoles and BIC. First, the difference on radiation. If you want that the radiation is allowed, it can be achieved by only destructive interference of all multiples at the same time. Anopole did, but it does not happen on BIC. Second, for any photonic structures, BIC represents eigenmode of the system. However, it is not the necessary condition for observation of anopoles. Third, difference on energy. In anopole, when electromagnetic energy is accumulated, it scatters, but the total electromagnetic fields outside the scatters mimic the incident field without distortion. On the contrary, since BIC proceeds in finite Q factors, they cannot couple to radiation channels and accumulate energy when excited from the far field. Next, important topic, we will introduce you some applications. A field enhancement up to several times was obtained due to excitation of the anopole state in isolated nanoparticle normally. This enhancement is guarded by the interference, which cancel each other but mutually enhance the field inside the resonator. Higher field enhancement was reported for individual slot nanodisk. The enhancement was improved by taking advantage of the high reflective index of the material by designing air hole in the nanodisk. Field enhancement in high-index dielectric meta-surface with gap meta-atoms at the anopole can up to several thousands. The quality vector Q vector, which governs the performance of any resonating structures. This idea is by increase the Q vector. When high Q vector approach 1 million, near field enhancements can up to 10,000 times. In BIC, we can use the same way. We can increase the Q vector by tuning the resonator parameters appropriately. Although the times of field is not mentioned in the studies, but with such a high Q vector, I think the result should be impressive.
The first I introduced the nonlinear harmonic generation. We want to get high Q vector and strong field enhancement. So in this part, we are aiming to enhancing the efficiency of nonlinear light-matter interaction. And I showed 3 mechanisms and 3 material optimization way to improve. In mechanism, the first is higher order nanopore supported by larger germanium and nanodisk, using the characteristic of narrower scattering cross-section and the higher localized field in confinement, just like picture A elaboration. Structure composed of a starch silicon nanodisk. This system is able to sustain the nanopore state. We get a result of it generates a conversion efficiency 1 order of magnitude higher than that observed for third harmonic generation at 500 nanometer. And the second is placing a silicon nanodisk on the top of gold reflector. Using the characteristic of metal has free charge oscillations at the interface, we get a result of the highest THG conversion efficiency of 0.01% was experimentally achieved. Last but not least is progressing a fabrication on ion beam bearing 2 slice nanowire, and the result turned out that it may generate different design of arrays and lattice of nanodisk. In material, the first is quasi-BICS in periodic arrangements of asymmetric meta-atoms. We get a result of that enhance the efficiency of nonlinear harmonic generation in meta-surfaces. And the second is 2 instant waves give rise to 4 waves. Using the characteristic of the frequency generation in 2 coupled resonators supported by BIC, we get a result of that it provided a way for optical generation of waves with ultra frequency. The last is isolated sub-wave length, ALGAS nanoparticle be given. Using the nonlinear effect and success predict a record high conversion efficiency for nanoscale resonators. As picture B and picture C in the elaboration, compare picture B, we can find picture C have obvious high peak. The second, I introduce the metamaterial and metasurfaces, and my aim is to bring the unique properties of nanopores to the microscopic scale. Method we use is to analyze toroidal dipole moment in metasurface at different frequency ranges, and I put 4 parts. The first is mathematical. I sought for metallic prismatic dielectric part. In metallic, the moment losses in metal part play the dominant role in the visible and near infrared regions. In prismatic, the performance of prismatic metamaterial is not so high in radio frequency. In metasurfaces, demonstrate strong toroidal response. And the second is metasurfaces. The mechanism is instant wave, linearly polarized along the central while induce the imprint toroidal moment, which is compensated by the electrical dipole moment. the result of the metasurfaces consisting of silicon spilled nanodisk arrays demonstrate a high Q factor and its application. Metasurfaces composed of perforated 100 nanometer thick silicon layer, as Figure A elaboration. It composed of planar 100 nanometer thick silicon layer with cylindrical perforations. The other application is the chain of dielectric disks guided by antipole excitation was shown. That such waveguides are extremely robust against physical bending and spilling, and that the antipole state is efficiently transmitted through the S-shaped and Y-shaped spiller, as Figure B elaboration. S-shaped and Y-shaped. And the third is radiation. Its definition is scaling the single resonators into periodic arrays, resulting in the appearance of collective interfaces phenomena not inherent to single resonators. In Lucy's radiation study, Figure C shows the dependence of the radiation Q factor of the leaky mode in the 1D array of dielectric spheres. One can see that radiation losses disappear only at a certain value of the Brahe wave number, which the leaky mode turns into the accidental BIC with non-zero group velocity. A true BIC exists only in an infinitive long chain when the radiation losses are completely cancelled due to the destructive interference just in Figure D. The Figure D shows the long chain. And the last is high Q in BIC. Definition: in symmetry protected BIC consisting of several tens of disks behaves as an infinite one, and thereby the number of disks are proportional to Q factor, as the Figure F shows. The number of disks is proportional to Q factor. And next is reduced Q factor. High Q resonates in such seemingly different metasurfaces with broken symmetry meta-atoms, but it can be unity by the BIC concept. Resonance originates from symmetry-protected BICs, transformed into quasi-BICs due to breaking of the in-plane inversion symmetry. So we put this concept in manipulation, using scattering light in broken symmetry metasurfaces, just as Figure G. Figure G shows the broken symmetry metasurfaces and the designs of the unit cell of a symmetry metasurfaces with a broken in-plane inversion symmetry, just as Figure H. And you will find the typical behavior of change of the reflectance spectrum from the metasurfaces with symmetry geometry alpha equal to 0 to a broken symmetry metasurfaces alpha equal to 0.25 is shown in the figure. The figure has alpha equal to 0 and alpha equal to 0.25. So I will make short conclusion. Q factor dependence on the asymmetry parameter was analytically and numerically proven for arbitrary metasurfaces with small and moderate degree of asymmetry. And last, I will introduce novel concept for lacing. The abstract is the strong field confinement associated with antipole and BICs stimulated the design of new type of nano lasers. We try to stimulate emission to amplify an enable state, so we generate a mode-locked signal in nanowire. In Figure A, an InGaAs nanodisk is placed in the middle of the optical circuit composed of 4 silicon nanowires. And in Figure B, by pumping linearly polarized light onto the nanodisk, the enable mode can be selectively excited with the nanodisk. By pumping the scattering mode of the InGaAs structure, no couple-in occurs, just shown in Figure C. In Figure D show an enable chain of weakly coupled nanodisks generate a model-locked signal propagating in the nanowire channel, and so does Figure E and F. Path trains of different periods generated by acting on the chain geometry. And I make conclusion. Numerical simulation showed that the enable chain behave very closely to an optical neural network, opening also future application of enable for optical integrated neuromorphic photonics circuits. Next is BIC for lasing, using the array of connecting semiconductor nanodisks shown in Figure G. With thickness of 300 nanometer and ready vary from 500 to 550 nanometer by decoupling from the radiation continuum, and is found an optical radius for 528.4 nanometer for the Q factor, which corresponds to the geometry for which two modes close to excitation frequency create BIC states. And here comes the question, how to affect lasers angle and wavelength? And I saw it in 3 points. First is the geometrical parameter of the lattice. Figure H sketch of the nanoparticle lattice grown on the quartz substrate. Second is the peak of the gain spectrum of GaAs. The third is the temperature range of operation in this work, limited to 77 to 200 K. And here comes summary and outlook. In the final, I will make a summary, include achievement, high index dielectric resonant structures, advantage, and future version. As above, we solve enhancement of electromagnetic field by rearrange the array of enable, and study of nonlinear and quantum effector in BICS concept, and further improving the value of the Q factor with the help of prismatic structures, and final confinement of light in high-index dielectric resonators with significant advantage for integrated photonics application. In dielectric resonance structures advantage, we find there are some characteristics such as chip, scalability, and simple geometry structure that can be integrated into a chip circuitry. So we can find a future version that help to develop of other approaches for achieving high efficiency in all dielectric resonant optical structures. Has a great potential to open a new era for all dielectric meta devices in nanophotonics and meta optics. And thank you for your listening.